Hi, now we are discussing synthetic methodology of the organic molecules. The ability to synthesize a particular compound, that means the targeted molecule, from commercially available materials is the fundamental to nearly all the aspects of organic chemistry. Okay, right. So before entering into the synthetic methodology, we need to know the terminology of it. Okay, in that target molecule, the molecule to be synthesized, okay, is simply considered as target molecule, and the very important is retrosynthesis. Okay, retrosynthesis is the process of breaking down the target molecule into commercially available starting materials by functional group interconversion and through the disconnection. Okay, so it is simply considered as retrosynthesis. Okay, the breakdown of the targeted molecule into commercially available starting materials by functional group interconversions and through the disconnection. Okay, retrosynthesis involves imaginary breaking of bonds and conversion of one functional group to another by efficient reactions, and then using this analysis for forward synthetic route to the target molecule. Okay, so retrosynthesis is the emerging branch of organic chemistry nowadays. So if one have the command on retrosynthesis, so one can easily solve the organic part. Okay, right. So that's why it is very important in the purpose of solving organic problems in the standard examinations. Okay, right. Now, disconnection, imaginary breaking of bonds which leads to the simple starting materials. Okay, disconnection is denoted by this. Okay, right. FGI here. FGI indicates functional group interconversion. So the definition of it as conversion of one functional group to another functional group by means of effective chemical reactions is known as functional group interconversion. Okay, right. Next one is synthon. It is important word, synthon. So fragments resulting from disconnection of targeted molecule considered as synthons. Okay, right. Next, synthetic equivalent, actual substrates used for the forward synthesis of target molecule are considered as synthetic equivalents. Okay, right. Now, retrosynthesis, there are two possible approaches to get a retrosynthesis. They are disconnection approach and another one is strategic bond approach. Okay, right. And before that, so what is how to proceed retrosynthesis and what are the advantages of retrosynthesis, we can see in this slide. Okay, so retrosynthesis analysis, that means we need to start from the point, that is we need to select the target molecule and we should identify the functional groups or strategic bonds in the molecule. Next step is to disconnect bonds using known and reliable reaction. Next, repeat disconnection as necessary to reach the simple starting materials which are commercially available. Next, try to use at least one novel disconnection. Okay, and next check all the pathways of disconnection and choose the most attractive route to synthesis the target molecule, to synthesis of the target molecule. Okay, right. So what are the advantages of retrosynthesis? Here, retrosynthesis leads to readily available and inexpensive starting materials, efficient synthetic reactions, flexibility of modifications in the synthesis of target molecule. That means in retrosynthetic analysis, so we can disconnect the target molecule into many ways, right? So in many ways we can choose the appropriate or the most attractive route to synthesize the target molecule. So that's why there is a flexibility of modifications in the synthesis of target molecule. Okay, next, synthesis of analogs of natural products. So many natural products analogs are synthesized by the use of retrosynthesis. Okay, quick and elegant routes for the synthesis of target molecules can be achieved by retrosynthesis. Okay, right. Now, disconnection approach to get retrosynthesis. Now, in disconnection approach, first we need to do imaginary breaking of the target, imaginary breaking of bonds of target molecule. Next, the breaking route depends on cost of availability of reagents, means synthetic equivalence, cost of availability of synthetic equivalence, and the number of synthetic steps should be minimum in the breaking route. Okay, and we need to follow that one. Now just check the example of a disconnection approach on target molecule. So this is the targeted molecule. Now this is one of the approach in which here we have, first we need to check for functional groups. Here the target molecule is having hydroxy group on it, so there is a possibility of disconnection. So if you disconnect the target molecule in this way, so it is having negative charge, that means carbon ion, and it is having positive charge on it. Okay, so from this, so here these are synthons and these are synthetic equivalents or reagents. Okay, now another route in which this is having positive charge or carbocation and this is having negative charge. Okay, just check the synthetic equivalence for first route of disconnection. In this synthetic equivalent is available, but to make a negative charge on that benzylic carbon with hydroxy group, that means oxygen is having already negative charge on it and we need to produce negative charge on benzylic carbon. So this is difficult. So to produce or to get the reagent for this synthon is difficult. So that's why this approach of disconnection is not the proper disconnection approach to retrosynthesis. Okay, right, check another route. So this is second one. If you observe this, the first synthon having the synthetic equivalent as benzaldehyde. Okay, so we can get benzaldehyde in commercial. Okay, it can easily available, right? Now, so if we check another synthon here for its equivalent or synthetic equivalent, we can get Grignard reagent, right? So which can produce this synthon. That means here the carbon is having negative charge and magnesium gets positive charge here. Simply it is Grignard reagent. Grignard reagent is also commercially available. So that's why the second pathway of disconnection is more appropriate. Okay, because here the synthons having their commercial reagents or commercial synthetic equivalent. So this is the correct disconnection approach, and from this we can get the target molecule. Okay, in synthesis process, right? Now synthesis. So how can we do that? So Grignard reagent can attack on that carbonyl carbon, and from that followed by hydrolysis we can get the synthetic that means targeted molecule, right? So that is the appropriate disconnection process. Now strategic bond approach. So here in disconnection approach, it is favorable whenever the target molecule have functional groups. Okay, if functional groups are absent on target molecule, then how to disconnect? This is the question, right? So in that conditions, strategic bonds are disconnected. Okay, so which are the strategic bonds? Okay, so this is another question. Now, strategic bonds, so just imagine the bonds which on disconnection, if they give the simple starting materials, then the bonds are considered as strategic bonds, okay, which doesn't have functional groups. Now, E.J. Corey introduced some rules to identify strategic bonds. The first one, is there any symmetry element in the targeting molecule? We need to find. Okay, so consider this is the target molecule, and if the symmetry element is possible, then disconnect the molecule along the symmetry element. So if you observe this O-tanniferine, so it is having equal halves, so plane of symmetry is possible. Okay, sorry, not plane of symmetry. Here is a possibility of C2 axis. Okay, so by that, if we disconnect the molecule, it can produce the same equal halves. Okay, so by this, we need to check for any symmetry element in the target molecule. Now, second one is the problem like the one is already solved. Okay, if the compounds are structurally similar and if the synthesis of one compound is already reported, then the synthesis of other compound can be placed in a parallel manner. Okay, just check the examples here. Phenine. So phenine, if phenine already synthesized by using retrosynthesis, then cinchonin is easily gets retrosynthesized, because already phenine has a path of disconnection. So by similar manner, we can disconnect cinchonin with a small functional group conversion. Then we can get, okay, we can get a synthetic equivalence, and by that we can synthesize cinchonin. Okay, so that's why the second point is we need to check for the compound similarities of already retrosynthetic analytically synthesized molecule or target molecule. Okay, next one, third one is if the target molecule has a repeating unit. So if we have to synthesize the repeating units independently and allowing them to polymerize to target molecule. Just check the example. If you take cyclodextrin, the repeating unit is simple here cyclohexanol. Okay, so whenever we synthesize cyclohexanol, and it is easy to produce cyclodextrin by polymerizing it. Okay, right. Now, strategic bond rules, and he has also given some strategic bond rules. That means Corey has given. In that, first we need to remove labile group first. Okay, so labile group means simply the very reactive groups like lactones, amides, acetyl groups, etc. are to be removed during the first disconnection of target molecule. Okay, this is the point we need to remember. Next, remove chiral center. Many natural products contain chiral centers, right? So a major task is the generation of chiral center in a controlled and predictable manner. So that's why we need to remove the chiral centers. Okay, right. Now favor the disconnection which produces closely related intermediate. Just check here with example. Now in the first step, functional group interconversion takes place. That means the targeted molecule is simply dehydrated here. Okay, and then further, so disconnections, we can get synthons, and from the synthons we can produce synthetic equivalents. Okay, one is Grignard reagent and one is carbonyl group. So the reaction between Grignard reagent carbonyl group is simply possible. That is the common reaction we can see, we can come across, right? Now, so synthesis. So Grignard reagent can attack on carbonyl group of that substrate or synthetic equivalent, and by that 4+2 addition and reduction with palladium hydrogenation, we can get the targeted molecule. Okay, right. Now The fourth one is remove interfering groups. For example, if we consider the substrate on epoxidation with metachloroperbenzoic acid, so we can think the metachloroperbenzoic acid can attack on the double bond of the ring and it epoxide that. But it is having the more reactive carbonyl group on that substrate, so it interferes with epoxidation on the double bond. Okay, so the carbonyl group also reacts with metachloroperbenzoic acid, so that's why it interferes and it produces the different products which is not desired. Okay, in that conditions, what we need to do? So first we need to protect that more reactive carbonyl group or the interfering group. So to protect it, we need to add glycol here and protecting, that is used for protecting it, protecting the carbonyl group. After protecting the carbonyl group, we need to apply metachloroperbenzoic acid, then it epoxide the double bond of that ring. Okay, and further to cleave or to deprotect that group, we need to use that intermediate in acidic condition, that means H3O plus, so we can get the carbonyl group back again and we can get the final product which we decide. Okay, so that means simply we need to remove the interfering groups first, or we need to protect them. Now, a disconnection is always favorable when it gives a positive and negative species. Okay, a disconnection is always favorable when it gives a positive and negative species. So first check the substrate here. We need to convert it into, that means functional group conversion here. The double bond is converted to hydroxy group. That means simply on back of this step, the dehydration produces the targeted molecule here, right? So that's why here functional group interconversion, and after that by disconnection, then we can get syntons, and from that we can produce synthetic equivalents. Okay, so this is the simple synthetic equivalent, and on this synthetic equivalent, by applying base, it can abstract proton from that alpha methyl of that carbonyl branch on the substrate, and then the carbane can attack on the aldehyde carbonyl carbon, and then further under H2SO4. Okay, so simply by the elimination of water we can get the targeted molecule. Okay, so that means a disconnection is always favorable when it gives positive and negative species. Okay, right, next consider the disconnections which always decreases complexity of target molecules. Okay, consider the disconnections which always decreases complexity of target molecules. Okay, right, so just check the target molecule. Now if we disconnect the target molecule in these two bonds, so it can produce the substrate by which we can easily produce this targeted molecule, because so we are familiar with diene and dienophile reactions, that means 4+2 pericyclic or conceptor reactions. Okay, so that's why we need to follow disconnections with the decreasing complexity of targeting molecules. Okay, now always use the powerful reactions for disconnections. So the reactions may be different important reactions, so Diels-Alder reactions, aldol condensations, Fischer-Indoles, Birch reactions, Cope rearrangement, or different kinds of rearrangement, or any other very important reactions. Okay, so we need to follow the familiar and the most useful or most needed or simple organic reactions in the disconnections way or disconnection approach. Okay, right. Now